Okay, everybody, welcome to our second lecture in ECE 576, Information Engineering. Before we get started, does anybody have questions regarding the previous lecture or the quiz? Okay, so we'll continue our discussion this time on communication over noisy channels and the role of information theory. So let's do a quick review of, excuse me, I think there's an issue with the, okay, so let's do a quick review of what we saw last time. So we said that our goal is going to be able to achieve perfect communication over an imperfect or a noisy channel. So we also saw that a typical communication system has a few components, and this is really the baseline system that we want to look at. So a typical communication system, we said it has a source which is emitting some symbols, and that bit stream or a sequence of bits basically gets encoded. Right, so there's multiple functions of an encoder, which we will study in the later lectures. I briefly mentioned last time that an encoder can be split up into a source encoder and a channel encoder. But once this bit stream goes through the encoder, we refer to it as a T, which is the encoded sequence. And then this sequence goes through a channel. Okay, and while going through the channel, maybe some noise N gets added to it. And at the receiver, there's the symbol R that gets received. So after receiving the symbols, we actually decode them and get something out of the decoder, which is referred to as S hat. And really our hope is, that this S hat is approximately equals to S. Okay, so that's the typical communication system. And the objective here is how do we achieve perfect or reliable communication over a noisy channel. So in this system, basically what we received is actually the transmitted signal or the stream of bits plus the noise N. And remember that this addition is really modulo 2 sum, or depending on what type of data is being transmitted, this addition means different things. So modulo 2 in the case of binary data. So which means, if you add a 0 and a 0, you get 0. You add 0 and a 1, you get 1. You get 1 and a 0 to get 1. But if you add 1 and a 1, you will get 0, right? So it's not 2. Now, we briefly also discussed what the channel represents in this communication system. So really the channel is actually in abstract terms, it's a mechanism that tells you how the input is distorted or transformed during the transmission. So we discussed a binary symmetric channel, right? So referred to as the BSC. So it's a simplified representation of the channel or the channel model, and it looked like the following. So if there's an input X to the channel, which is binary, so it can be a 0 and a 1, that gets mapped to zeros and ones according to this diagram here. So there is a probability F that there is an error, and there is a probability 1 minus F that you get at the output exactly the same thing that you sent. Okay, so in other words, we described it in terms of the conditional probabilities. So we said probability Y is 0 given X is 0 is 1 minus F. And the probability Y is 1 given X is 0 is F. And the same thing for Y is 0 given X is 1. And probability Y is 1 given X is 1 minus F. Okay, so this is one of the channels that we discussed, but there can be many other channels. Okay, so I'm going to mention briefly what other channel types you might encounter during this course or in general. You could have something called a binary erasure channel. Okay, and what that means is that from a source X, the output can either be a 0, a 1, or an erasure, right? So erasure represented by E tells you so what happens is we have something like this here, and the probability of ending up in an erasure is F, and this is 1 minus F. So again, we will have different conditional probabilities here, saying probability Y is 0. Okay, first let's call it. And so the probability Y is 0 given X is 0 is 1 minus F. The probability Y is, Y is an erasure given X is 0 is 1 is F here. And probability Y is erasure given X is 1 is also F. And the probability Y is 1 given X is 1 minus F. So that's another type of channel that's possibly considered in theoretical analysis. And also I would want to mention another type of channel called the Z channel. Okay, so that's also, let's call it a Z channel. And the reason why it's called a Z is because the diagram looks like a Z. So we have, it's actually a binary asymmetric. Okay. So with the same diagram, X and Y, two input symbols, the diagram looks like a Z. Okay, so if you send a 0, it's always going to be received as a 0. But if you send a 1, it may be confused as a 0 with probability F. This is 1. So in terms of probabilities, the probability Y is 0 given X is 0 is 1. Probability Y is 1 given X is 0 is actually 0. And probability Y is 1 given X is, probability Y is 0 given X is 1 is F. And the probability Y is 1 given X is 1 equals 1 minus F. Okay, so any questions so far before we jump into today's topics? Okay, so that's the end of our review. And now what we want to look at is how do we achieve perfect?
I had a question in this quiz. This problem with the what problem was the? I emailed you, Professor. I think was problem 7.
Yeah. Can you quickly remind me of the problem 7? I can open it up also.
Yeah.
Yeah. So the question is about what does information theory help us with? So the options are determining fundamental limits of communication. Yeah, that is true. Identifying trade-offs in rate and error probability. Yeah.
Or the last one, finding the.
Yeah, it helps us in finding capacity of channels. It doesn't tell us how to find the encoding and the decoding schemes. But that's by trial and error. That's by using intuition. We will see this in today's lecture, starting with a very basic encoding scheme. So there's no standard way of encoding a sequence, right?
I was confused with the disclaimer you mentioned in the class where it says that it does not tell you how to achieve the limit, which is probably it's sort of the first option, you know, which does not tell you how to. Let me go here. Okay.
So it does not tell you. That means so information theory is helpful for everything except finding the encoding and decoding schemes.
Or the limit of communication. That's also a possibility.
No, I mean it is definitely
the fundamental limit. So that's why I got hung up on that limit where you mention it in the disclaimer, and which sounded me like the right. It's a wording type of confusion, you know.
Yeah, I see. I mean, the question is posed in an opposite way, saying except which of the options.
Right. So if you take option 1, it says determine the limits, and it does not tell you how to achieve the limits. So
No,
it's
but you can determine the fundamental limits.
but you mentioned in the disclaimer that practically it does not tell you how to achieve the limit.
Yeah, achieving is different than finding the limit.
Okay, so achieving, determining, kind of, you know, that's what I got hung up on that.
Yeah, I mean, we can discuss it after the class, but there was a
Okay.
slight caveat here.
Yeah, that's why I also emailed you about that.
So the question is, how do we achieve reliable communication over such unreliable channels? So several options can be come to mind. First, very naive sort of an approach would be thinking about, can we improve the channel? Can we make it more reliable? Right, but again, disclaimer, it's that it may not be under our control. Okay. I mean, you could obviously think about having a noise-free channel, but that's not in your control, and you have to live with environmental conditions that are available to you. Then another possibility is that you design an encoder that can help you detect and correct errors. Okay, so two important things. One is detection and the other is correction. Okay, so even though you've gone through a unreliable channel, so you may have made some errors. So is it possible that you had an encoding which can help you detect and even sometimes correct the errors that you made? So here comes the important thing that you should remember. So what an encoder will generally do is, and specifically about the channel encoder. So if you had a symbol S, which gets goes through a, let's say, a source encoder, then a channel encoder, and then goes through a noisy channel, and onwards to a channel decoder, then a source decoder to get S hat. The important thing here is that a channel decoder actually adds redundancy to the input data stream. So what it does is it adds redundancy to the original message. Okay, and what happens at the decoding part is basically you use the known redundancy to infer the original signal and noise. Okay, so important thing here is the known redundancy. So at the encoder, you add some redundancy, but at the decoder, you already know what type of redundancy you added. So comparing those, you can actually figure out what the message was, and you may even be able to correct any errors that were made. Also, as a side note, I would want to mention here that the source encoder actually compresses the data. So basically what it does is data compression. So any source you want to represent it as with the least number of bits, you do it with a source encoder. So once the data is compressed, you pass it through the channel encoder, and channel encoder actually makes it longer. It adds some redundancy to the bit stream based on what type of channel you have. And hopefully, if messages, compressed messages reconstructed at the channel decoder, then you can actually decompress your source to get your original message. So this may be doing a decompression here. Okay. So again, I would like to mention the same point that the student was raising here, that the information theory is actually a non-constructive theory. So it doesn't tell you how, it just tells you what. So it provides theoretical limits on communication systems. Right, so for example, it can tell you what is the best error correcting performance. We can get, okay, but coding theory, that's a totally different subject. We are just going to see a glimpse of it, but that's a whole different theory on how to construct codes and encoding schemes that can help you achieve something closer to the fundamental limits. So this explores the creation of practical encoding and decoding systems. Okay.
When we compress something, we just degrade the quality of that, and then when we decompress it, we put back that quality. Is that the?
No. So when we compress something, we just express it using the minimum number of bits possible. Right. So I told you last time that let's say you want to express the digit 4, right? So number 4 decimal.
Oh, I got it.
Right. So you can obviously send it as 1 0 zeros.
And you ignore the other.
Yeah, that's like one hot encoding. Right, but you can always send it as 1 0, which is a binary encoded sequence.
Right. Okay.
So this is compression. how do you represent your digits or the information. But
Yep.
sending 1 0, you have an, I mean, at the output, 1 0 may be received as 1 1. So if you want to, make sure that you receive the correct version, you may send 1 0 1 0. So like you repeat it twice. So hopefully one of them is 1 0.
Right.
So we are going to see this right now. So how do we do error correcting encodings?
Thank you.
Okay, so our next topic is the error correcting codes for BSC. So we are only looking at binary sources and symmetric channels. And if people want to refer to the textbook, I'm mentioning a reference here. This is going to be from chapter 1.2 from the McKay book. Right, so if you want to read offline, this is where you can refer to. So as I just mentioned, I think one way, very basic, naive way to reduce errors is by repeating information. So if you can understand what I said, I can repeat it 2 times, right? If you still can't understand, I can repeat it 3 times and so on. So that's something called repetition coding. Okay, so it's really a simplest way. It's not smart at all. So it's a basic way to add redundancy. To information. Okay, so for example, R3 repetition code repeats everything or every bit 3 times. Okay, so if I were to send S, which is the source symbol, and let's say it was a sequence 0 0 1 0 1 1 0 and R3 encoding looks like the following. The original message is 0 0 1 0 1 1 0. Then if you send the data using an R3 encoding, you will repeat each bit thrice. So you will send a 0 0 0 here, then 1 1 1 here. Okay, so hopefully at the receiver, even if some of the bits get corrupted, you can still make out what the original message was sent. Okay. So consider if this is what you sent, and let's say it went through some example noise, right? So noise can also be in binary digits. So let's say the noise was 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1. Okay, so at the receiver, so the received message, and by the way, let's call this S, this as the T, this is the N, and this is the R. So R is just the T plus the N. So what you will receive at the receiver will be just the addition, which is zeros here, 0, 0, 1 here, 1, 1, 1. Okay, so now here we're going to have flips. So we will have a 0, 1, and a 0. And then the rest is all the same as the original message. Okay, so if you look at this sequence here, obviously you know that for correct transmission, all three of them should be the same, right? Because you just repeated the bit. So this looks correct, this looks correct, and this looks correct. Okay, this is true. So these bits, right? Or this piece may be in error. Okay, so there is some error here. But what is the error? Well, an optimal detector for an R3 sequence is just called the majority vote. Right? There's nothing better you can do. So if so in the case here, you have 2 zeros and a 1. So most likely you were sending a 0, and somehow one of them became a 1. But this logic does not apply to case here, because you actually sent a 1, but now the majority is 0. So the trouble is, some errors may not get detected. So in a majority vote, what you actually do is you derive by comparing the or you determine the most likely, right, symbols sent based on majority rule. So in this case, I mean, from here, what you can say is that your S hat is actually telling you it's 0, 0, 1, 0, 0, 1, and a 0. So that's the output of your detector. So what we see is that this error has been corrected. But unfortunately, the bit here, we couldn't even detect that there was an error. Okay, so we have just seen a very simple example of an encoding scheme, and we've seen its strengths and weaknesses. So if you have an R3 scheme, you can only detect one bit errors and correct them. So note, not all errors can be corrected using repetition. So for example, an R3 code can only detect one bit of errors. Okay, so I mean, looking at this, all of you are smart, so you can obviously ask, why don't we just increase the repetitions? Why stop at R3? Why don't we have R100, R whatever? I mean, large number of R's. So can we? Because obviously it makes sense that more repetitions is going to reduce the errors, and hopefully the majority vote may also give you better results. So can we increase the repetitions? To get better performance? Okay, so for example, R5, R7, R9, etc. And the answer to this is obviously you can, but we will lose on the rate of information transferred. Okay, so if you're trying to send one bit of information and we do it 100 times, obviously you're only just sending one bit, so you're losing time. We wanted to transmit more bits, but since a lot of time is spent on just sending one bit, so that reduces your rate of information transfer. That's not desirable as well. So in essence, basically, there's a trade-off between the rate and the probability of error that we can achieve. So this simple example has revealed that there's a trade-off between the probability of error and the rate of information transfer. Okay, so let's say let's call this probability of error as BB, which is the probability of bit error, and let's call R as the the rate of information transfer. Okay, and that's bits per unit time, and the probability is just a number between 0 and 1. Now, if you want to find what the probability of error is, let's write down a formula here. So PB is actually, so let's say we want to calculate the probability of bit error with n repetitions. Okay, so essentially what you're doing is you're sending the same bit again and again. So you may receive zeros, zeros, ones, right? Sometimes it's an error, sometimes it's not, and so on. So these are n repetitions for one bit. So if you have a scenario like this, I think the binomial random variable is one of the best to model such a scenario. So if you want to find out the probability of error happening in an encoding like this, basically it's really the binomial probability, and then you add them up. So so it's n choose n, probability of error, which is f, that's power small n, and then 1 minus f, that's power n minus small n. Okay, and this happens over a summation. Summation is over a majority vote, right? So you only have an error if majority of your bits are in error. So you have to sum over the possibility that more than half of your bits are in error. So that will be n plus 1 over 2, right? To up till n. So this summation summation is to have in error for an Rn repetition code. Okay, so I hope this is it's not too hard to understand. So I mean, if you send n bits and small n of them are in error, this thing is the probability that small n bits are in error in a sequence of n bits. That's a simple binomial random variable. But obviously, you want to have majority of them in error to actually make an error, because it's a repetition code. So then you have to sum over all those cases. So that means more than half of the bits have to be in error. So we add from n plus 1 over 2 up till n. Okay, so let's see the trade-off that we talked about in a little more detail. So consider a graph of the rate of information and the probability of bit error. Okay, so let's call it PB, which is the error probability. So assuming that we are looking at a binary symmetric channel, right? So with some error probability, let's say it is 0.1, right? So assuming you have a binary symmetric channel and the error probability is 0.1. Okay, so if you send one bit of information every unit time, whatever the unit of time is, but if you send one bit each time, your rate is 1. Okay, so you are at rate 1, and the probability of bit error in that case will be 0.1. So that's a point here. And this is really a code that's called an R1 code, meaning you're not repeating anything. Right, so it's an R1, or in other words, transmission without repeating. Okay, so you've done nothing. You just transmit one bit as it is, and you're passing it through a binary symmetric channel. That channel has an error probability of 0.1, so that's the best you can do. But now, let's say you start implementing your repetition code, and you come up with an R3 one. So what happens is you're repeating every bit 3 times. So immediately your rate has become 1/3. Does everybody see that? So immediately, once you do an R3 code, your rate has reduced from 1 bit per second or 1 bit per unit time to 1/3 bit per unit time, because let's say, so let's say this is your R1 code, and this is the time window. Okay, so and in R1, you're just sending 1 bit in this time, right? Oops. So let's say unit time window. Okay, so R1 is going to have 1 bit sent here, but R3 is going to have 1 bit sent here, where it has repeating every time. So the rate here is 1, and the rate here is 1/3. And obviously, if you use an R5, you're actually going to a 1/5 kind of rate. So if you use the R3 repetition code, your rate obviously reduces, but you're gaining on the probability of error as well. So if you compute it using this formula here, it will come out to be something close to 0.03, right? So you go here to 0.03. So you actually improve in both the rate and the probability of error by using an R3 encoding scheme. Now, obviously, you can ask what happens if you, use an R5. So R5 is it's going to reduce your rate to 1/5. So you're going to come to about a 1/5 here. Okay, and obviously your probability of bit error is going to reduce, and it's going to come just somewhere to 0.01, right? So it comes somewhere here, the R1. And if you keep doing more and more repetitions, at R69, you're almost, close to 0. Right? So this is R69. Okay, so what you see here is
The R1 and R5, the middle one.
Yeah, sorry, this is the R5. Thank you. So, I mean, there is some trade-off. It's maybe not a straight line here, but just to show it to you, that there is a kind of trading off going on. If you want to reduce your error probability, you actually have to sacrifice, in your rate.
Is that converted into the bandwidth, Professor, or?
Yeah, obviously that translates into bandwidth.
Okay.
I mean, bandwidth is the wrong term to use because that's the characteristic of the channel. So channel can kind of transmit some information or not, but this is really what you're achieving when you send some information. But essentially the same thing, the speed of information transfer.
Okay, yeah.
You're reducing that, and obviously you're getting more reliability, but you need to increase the data rate as well. So at least for a very basic code, we have seen, there is this phenomenon happening. And the question is, that question is a lot of coding theorists try to work on these problems, and they ask themselves, how do we, how do we increase the rate? Let's say you want to achieve the same probability of error. Is there something better than R3 I can do? Right, having the same error probability, but getting some better rate. Right? So I want to move, let's say on a horizontal line, I want to move here. Right. Let's say I have a low enough probability of error, but is there a way that I can push that towards the higher rate? And again, there are possibilities. People have figured out ways to do it, but the maximum you could do is kind of the Shannon limit, and that's the subject of information theory. Is there a maximum point here that you can find. That's called the C. That's the Shannon capacity, or the capacity of the channel. And the question is, how do we find it? Right. If I give you any channel, can you find me what's the capacity? What is possible to achieve in that type of channel? The how is the big question, but can you just find me the C? That's the goal of information theory. So anyway, let's look at a slight improvement over repetition codes. So it starts with a question where you want to know, can we improve on repetition codes in terms of the error probability and rate. So remember that whenever we want to encode information, we also want to ensure that that encoding has an equally practical decoding scheme. So in the case of repetition code, you can easily decode it using a majority vote. So that's a very simple decoding scheme that we have. So whenever we want to develop a code or an encoding scheme, you want to make sure that it's also decodable, right? You just can't arbitrarily say, okay, just do random operations on the bits and it becomes an encoding scheme. Obviously, it does become a scheme, but you may not be able to retrieve the information from it. So one slightly advanced way is to do block coding. Okay, so again, that's a natural thought. I mean, if people say you encode single bits, then people might also think, why don't you encode a block of bits or a group of bits together? Okay, so that means you add redundancy to a block of bits. So hopefully that improves the rate a little bit. And the question is, can we also do better in terms of the probability of error? So let's investigate what are those schemes and how do they work. So one scheme, or one of the simplest schemes in block coding, is called the 7-4 Hamming code. Okay, so what does 7-4 mean? That means if you have 4 bits, you make them 7, right? So 3 of them will be parity bits. So you take blocks of 4 bits and encode them into 7 bits using simple parity. So for example, if S is a 4-bit sequence, which is S1, S2, S3, S4, right? 4 bits. So if this goes through a 7-4 Hamming encoder, the output will be T will be the first 4 bits as it is, so S1, S2, S3, S4, and then you will have T5, T6, T7. These are the parity bits, but all in all, these are 7 bits. Okay, so the 7-4 Hamming code is generated in the following way. It's a very natural way of encoding a block of bits. So T, which is S1, S2, S3, S4, those are the source bits, and T5, T6, T7. So basically, you take 3 at a time. So you have the first 3 bits, they're going to give you, if you add them up, they're going to give you the T5. That's the parity generation, parity bit generation. Then you take the next 2 bits, right? And those will give you the T6. And finally, the you will have first one and these 2, right? So you add them and then you get the T7. Right, so I can write this more formally here. How do we generate parity bits? Basically, T5 will be S1 plus S2 plus S3. And again, this is a modulo 2 sum. T6 will be S2 plus S3 plus S4. And the final parity bit will be S3 plus S4 plus S1. Okay, so we'll see this in a little bit more detail in today's lecture. But before delving into the details, I think I want to mention here that the rate of 4-7 or 7-4 Hamming code. Can anybody guess what the rate of a 7-4 Hamming code will be? So remember, we we said that the rate of an R1 is 1 because we transmit 1 bit in 1 time slot. And in a Hamming 7-4 code, we're actually transmitting 4 bits, right? But we're using 7 slots.
So 4/7.
Yeah, 4 by 7. So it's actually right. So let's right. So number of information bits, and these are the number of bits used to transmit them. Okay, again, I'm going to highlight this. Okay, so the Hamming code is at least the 7-4 Hamming code can be represented in a Venn diagram as well. So So you can have like a circle. Okay, so we can have 3 circles, and we start filling it up like the following. So we have S1, we have S2, S3, and S4. Okay, and the sum of S1, S2, and S3 gives you the T5, and then S2, S3, and S4 get added to T6, and S3, S4, and S1 get added to T7. So, I mean, this simple diagram can also be used to generate those parities. Now, as an example, so let's say your S is 1000. You want to transmit 1000. What will be the Hamming 7/4 code? You can again draw this figure here. Okay, so you start filling that up. So you start here 0. Oops. Sorry, the first one is 1, 0, 0, and a 0. And then the next are just parity bits. So you add each of the bits in the circle. So you will get a 1 here, a 0 here, and a 1 here, right? And then you can just write that out. So T will be the source bits as it is, 1, 0, 0, 0. T5 is 1, T6 is 0, and T7 is 1. Okay, so that's your Hamming 7/4 encoding for the block S. Now, I will mention some properties of this code here. So properties of a 7/4 Hamming code. So number 1 property is that any pair of code words in a Hamming code differ in at least 3 bits. And maybe I should mention, instead of saying any, but we can say adjacent, right? Well, I mean, it has the same meaning because you're saying at least 3 bits. So I can write it, I can give you a table mentioning the code words. So if, let's say, these were the source messages, and these are the transmitted ones. So for a source message of 0000, you will have, I'll do it just for a few binary source messages. So you will have a transmission, which will be 4 zeros and 3 zeros parity bits. For the second message, you will have 0001 and then 011. And then the next one will be 0010, and parity bits are all ones. For the next one, it's 0011, 1, 0, and 1. Okay, so the key here is to notice, obviously this can keep going on. Notice that the encoded sequences have differences in at least 3 bits or 3 places. Right, so if you look at the first and the second, you will see that there's a difference of 3 bits. And if you look at the second and the third, this is different, this is different, this is different. So adjacent code words are actually differ. They differ by 3 bits. That's a good property to have because it's not easy to confuse one with the other. You will have to make 3 errors to actually get confused completely with another sequence or symbol. Okay, and if you look at the
Actually, one question. On the last line there, can you show how we calculate that last bit? Because I got something slightly different. I got 0 instead.
Okay, so we have this. So the first 4 of them are just copied directly, right? 001.
Right.
Then the first parity bit is just adding these 3 up. So that's giving you. Sorry, yeah, that's giving you 1. Then the second one is just adding these 3 up. Oops. So yeah, you were right.
Okay, just want to make sure I'm not incorrect.
Thank you. Yeah. So we have a difference of 3 of them are different, right? Okay. So look, 2 input symbols that are different by just 1 bit. Actually, in the encoded sequence, they differ by 3 bit. So I can just add this as a comment here. Okay, so this is the first property. The second property is that the Hamming code is a linear code. Okay, so in other words, it can be represented as can be written in a compact matrix multiplication form. So it can be written as T is some G times the S, right? So S is the source. And we can always make them vectors. So source, message, vector, and this is the transmitted or let's say encoded sequence. And this G here is your generator matrix. Okay, so if you want to write down the G explicitly, it's easy to do so because what you're doing is you just take the first 4 bits of the source and copy them as it is. So the first 4 rows of the matrix G will just be an identity matrix. Okay, and the next 3 will show how your parity is generated. So for the first parity bits, you add the first 3 source symbols. So you will write a 1, 1, 1, 0 here, and then a 0, 1, 1, 1, and the last one will be 1, 0, 1. Okay, so essentially what you see is here the first 3 are added, the last 3 are added, and then these 3 are added. Okay, so if you look closely here, this part is simply the identity matrix. Right, so it helps to copy the first 4 bits. And then this part here is actually generating the parity. So essentially, if you just multiply this matrix with any 4x1 source message, you will get a 7x1 vector of the encoded sequence T. Okay, so the reason we want to have such properties is because it's become really easy for computers to encode messages. What you do is just matrix multiplication for every block of source messages. So matrix forms makes it convenient for computers to implement the code on a computer, or implement the code. And the second remark here is, having codes can be generalized to different block lengths. Okay, so for example, you can have an NK Hamming code. With a block length K and encoded length N. Okay. I mean, it's really natural extension of the Hamming code. Okay, so up till now, what we have seen is, going from simple repetition codes to encoding blocks of messages, and that's called a Hamming code. But just like we did for the repetition code, we now want to also decode the Hamming codes. So let's talk a little bit about how to decode. Okay, so it's an obvious remark that once you make the encodings more complex, then the decoding also gets more complicated as the coding complexity increases. Right, so obviously you can come up with any type of encoding scheme, which may also be great in terms of the error performance and rate, but you may not know how to decode it. So then that's not useful. So another concern here is, anything could have, or any bit could have experienced errors. So even the parity bits may have errors in them. So note that any bit could have been flipped during transmission, including the parity bits. So you have to be mindful of that fact when you talk about how to decode the codes. And one way, to look at decodability of encoding schemes is to see how far the received message is from the original message. Right, so, or the original code words. That's called a distance-based decoding, right? So once you receive a message, you can actually find the distance, and that's called, if you look at the number of bits that are different, then that's called the Hamming distance between codes or the code words. I can mention it briefly here. So for example, we can look at how many bits are different in the received message compared with the code words, right? So that's referred to as the Hamming distance. So your message is actually decoded to the closest code word in terms of Hamming distance. So if you differ with the code word by 0 bits, you're actually exactly that code word. So you're detected as that code word. But let's say you differ with one of them in 1 bit and the others in more, then naturally you will say that we are closest to this code word, so therefore we detect that code word. But a more efficient way, can be using a method called syndrome decoding. So more so it's and unfortunately or fortunately it can only correct 1 bit of errors. Just like our previous repetition codes. So let's take a look at what syndrome decoding is before we end today's lecture. So that's going to be our almost the last topic that we will talk about. So syndrome actually refers to violations in parity. So once we have a received sequence, we will look at how many parity violations are there, and then we will match the sequence to the most likely code word that was sent. So this syndrome here is actually it's a violation of parity bit or parity bits. Okay, so assume that the received signal R is R1, R2, R3, R4, R5, R6, R7. So you assume that we receive 7 bits. So if you go back and look at the Hamming code diagram, you will see you can map these digits onto the diagram, and what you will get eventually is R1 here, R2, R3, R4, and then the 5th one is here, then 6th here, and the last one here. So this is called our first parity circle. This is the second parity circle. And this is the third. And all of them have to agree. So all the 3 circles have to be consistent in terms of parity in order for an accurate detection. So imagine we have a received signal. So we'll take an example here where what you get, let's call it example 1. So what you received is 1 1 0 0 1 0 1. Okay, so you can again draw this figure and try to fill in the circles with the numbers and this received sequence. I'll try to do it with you. So the first one is 1, and then 1, 0. Then we have 0. So these are the first four bits, and then 1, 0, and 1. That's how we fill this circle. And now look at the parity status. So if we consider the first parity circle, the parity does not agree, right? So if you look at this, we look at this circle, adding these three up, actually it does not lead to 1. So parity bit is in error. Now if you look at the second one here, again, the parity bits do not agree, right? So this again has an error. So looking at these two, oops. So now, because two of them are in error, so what you can say is basically this is really the culprit here. Right? So if this were to be 0, all the parities will agree. The third parity circle is already fine. So in the two circles that do not agree, the bit that's common to them is actually an error. So if you use syndrome decoding, it tells you what the error actually is, assuming it's just a 1-bit error. If we had more bit of errors, then it may not be possible. So the syndrome can be written as, syndrome is referred to as Z, and it's 1, 1, 0. So what this means is that the first parity violated. This says that the second parity is violated. And this means that the third parity is okay. Okay, so syndrome tells you whether there's a issue with the parity or not. So in this case, the syndrome Z is 1, 1, 0. Now let's take another example here. So in example 2, our received message is 1, 0, 0, 0, 0, 0, 1. Now, again, if you want to analyze this received message and see what was transmitted. So actually, by the way, if in the previous example, you want to see what's transmitted, that's easy to find out now. So therefore, the decoded sequence is, okay, so decoded sequence will be what? So it's 1. There's 1, 0, 0, 0. And then 1, 0, 1. Okay. Hence the decoded message is S hat is 1000. Okay, so we've actually fixed this error here. With the help of parity, we were able to detect 1 bit of error. Now, going to the second example, again, we can draw a circle, actually 3 circles. Okay, and start filling it up. So we start with 1, 0, 0, 0, and then our parity bits are 0, 0, and 1. Okay. So,
How did you come up with z equals 110 to the syndrome?
yeah, so Z is telling you which parities are in violation. So if you look at the first parity circle, second parity circle, and third parity circle, 1 means that there is a violation. 0 means that there is no violation. So I'll actually give you a syndrome table after this, so you'll have an idea of what is going on here. Now looking at this example, I think if you start with the first parity circle here, this does not agree because 1 plus 0 plus 0 is 1, but it's not the case. So what you will have here is the first is in error. Looking at the second one, second is okay. Third is also okay. So basically what your syndrome Z is actually 1, 0, and a 0. So essentially this does not agree, right? So if this does not agree, that means, this may be wrong. So here's the source of the error. So I need to fix this. So our syndrome says first parity is violated, and the other parity are okay. Right, so if you want to go back and see what the decoded sequences, it will be 1, 0, 0, 0, and then you will have 1, 0, 1. So S hat will be 1, 0, 0, 0. Right, in this case, only the parity bit was in error, so the message was already okay. So we left it like that. Another example where you will have a different type of error. So let's consider your received sequence is 1, 0, 1, 0, 1, 0, 1. So to analyze this, you can start with the circle. So you start labeling it. So 1, 0, 1, 0, and 1, 0, 1 finally here. So starting one by one, you see this first circle does not agree. Let's just label it like this. So that means there's an error here. These have issue. Looking at the second parity circle, it also does not agree because 0, 1, 0 should add up to 1. So that's again in violation. Oops. There was an issue here. There was some trouble here. And the third parity circle also does not agree because 1 plus 1 plus 0 should have been 0. So all three of them are in error now. Right, so so we have an issue here. So essentially what we see is that the issue is with this bit, because if you were to replace this, then everything will be okay. Or let's call this the error bit. So in syndrome, in this case, is 1, 1, 1, which essentially means that all parity bits are violated. Okay. So if this was the case, then the decoded sequence is 1, 0, 0, 0, 1, 0, 1, right? So you fix the third bit here, and therefore S hat will be 1, 0, 0, 0. Okay, so we've seen three cases where we will have different type of errors and how we can detect them using syndrome decoding. And the purpose of having syndrome is that once you figure out what the syndrome is, you can actually use a lookup table to fix the bit. So in general, the syndrome decoder table is as follows. So if you have a certain syndrome value, you can actually unflip a certain bit. So the possible syndromes are 8 of them, right? So 1, 2, 3, 4, 5. Okay, so syndrome can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So if syndrome is all 0, that means all parity bits are okay, then you don't have to do anything. So you don't unflip anything. If it is 0, 0, 1, then you have to flip R7, R6, R4, R5, R1, R2, R3. Obviously, you don't have to have this table available at all times. You can again draw a diagram like this and try to figure out which one is the source of error that can fix the parity issues. So you don't need any table, but this is one convenient way. If you just figure out the syndrome by looking at the received sequence, because figuring out the syndrome is easier. You can just look at the 4 bits and figure out the parities. So you add 3 of them, see whether the first one is satisfied, then the second one, and then the third one. So figuring out a syndrome.
Whichever circle is affected, right, by the source of error or the error bit.
Yeah.
Okay.
So I mean, you don't have to draw this circles every time. If you can figure out the syndrome directly, then this table can help you fix the bit. Okay, so what we have seen today is really some basic schemes on encoding and decoding and the fundamental rate and probability of error trade-off. So I'm going to write the question that we are interested in. So we want to know what performance can the best encoder in the world possibly achieve, right? And we have seen that there is a trade-off. You just can't have best of both worlds. So trade-off between the decoded bit error probability and the rate of transmission. And the question is, what pairs R and PB are possible? Right, so that's the big question, and that's where the whole purpose of this course lies in. So I'm going to briefly introduce this today, and we'll perhaps delve into more formal details in the upcoming lectures. But going back to the same diagram we saw earlier today, we have this figure where we can plot the R or the rate against the PB, and assuming the channel is a BSC with F equals to 0.1. That's our assumption. You can have any channel, but the idea is similar. You'll have a figure which tells you what's the rate and probability of error that is possible. So we saw today, you have 1 here and a 0.1 here. So at rate 1 with a probability of 0.1, we saw that the R1 can achieve, or repetition code can achieve this. Right, so that's a possible point we can be at. But that's not very ideal because we our rate is 1, but our probability of error is very high, which is about 10%. So what we saw is we can reduce it, but we'll also have to compromise on the rate, which becomes 0.33, but the rate also reduces. So we go somewhere, let's draw here. So 0.05. Okay, so we go somewhere around 0.03. Somewhere here. That's called the R3. R2 is at 20% the rate, and somewhere here. That's R5. And keep doing it, R61, 69, this is somewhere here. So your rate is also very, very little, but you have almost zero probability of error. Now, we studied a Hamming 7.4 code as well. So where does that go? So obviously its rate is 4/7, which it's about 0.57. So we are almost here, and the probability of error is close to 0.06. So I haven't shown you the computations, but if you do, you will find out that we are almost here. So it's the 7.4 Hamming code. So obviously everything in between is somewhere, along these lines. So we can have different repetition codes, different NK Hamming codes. Again, K over N is going to be the rate. So whatever you choose, it's going to have a point somewhere here around the space. But what I want to show you is that the whole information theory is about figuring out this thing here. So there's a point that's called C, or the Shannon capacity. Right, so beyond which you cannot achieve anything. So obviously R1 is achievable, but anything below this here, this part is not achievable. That's the beauty of Shannon's theory. So this region here is not achievable. So for a zero probability of error, you cannot achieve anything higher than C. C is the maximum rate at which you can transmit. What that C is depends on what channel you have. So in this case, we are using a binary symmetric channel. So it has its own C. If you're using the binary erasure channel, it has a different C. But the whole idea is there is a line that you can draw between something that is achievable and something that is not achievable. Okay. C is that fundamental point where you can achieve perfect communication. So if you want to achieve perfect communication, error-free, your rate has to be less than C. Right. Now, this theory is just telling you that there exists a C. It doesn't tell you how to achieve it, right? We just saw some codes, we saw repetition codes, we saw Hamming code. Those achieve different points. They don't achieve the C, right? So that's the job of coding theorists, designers, to come up with codes that can be decoded and still achieve the performance. But the goal of Shannon and this theory is to draw that line that separates between what is achievable and what is not. Okay, so I'm going to write here the Shannon capacity more formally. So it's the maximum rate at which communication is possible with arbitrary small dB. It is also called the capacity of the channel. Okay, and I'm going to also mention the Shannon's noisy channel coding theorem. So we haven't seen any of the mathematics behind the Shannon's theory yet. It's going to be coming in the upcoming lectures, but just to give you a flavor of what type of conclusions we can come up with using this theory, I think it's very important. So this theorem says that information can be communicated over a noisy channel at a non-zero rate with arbitrarily small error probability. Okay, so the whole idea is that there is a possibility of having an encoding scheme that can communicate information over a noisy channel where the rate is non-zero and the probability is almost zero, right? So there's a C that exists. Now, the whole point is if you go tomorrow and in the next lecture, you come up with a scheme telling me, you know, professor, I invented a new encoding scheme that achieves a error probability and rate, which is here, I will say that's not possible, right? Because that's the whole proof of this theory. If you're considering a binary symmetric channel, I think there's the best thing you could do is C with the zero probability of error. But obviously, if you're willing to compromise on the error probability, you can, you know, improve your rate. But still, there is a line that you have to draw. You just can't achieve the best of both worlds. You cannot have a, you know, a rate of 1 and a probability of error which is 0. That's simply not possible. Okay, so for a binary symmetric channel, this is just an anecdote here. The Shannon capacity can be calculated so the C for BSC is 1 minus F log 2 1 over F plus 1 minus F log 2 of 1 over 1 minus f. Okay, so we are not going into how we got this. Hopefully, after a couple of lectures, you should be able to compute it for any channel, even for a binary symmetric channel. But to show you, this expression gives you what the maximum capacity of a binary symmetric channel is. And it's obvious that it depends on the f, which is the error probability of the binary symmetric channel. So if you change f, again, if the error is very small, then the capacity is it's very high. If error is large, capacity is low. So this thing in here is something called the entropy of a BSC. Again, entropy is a technical term, and we are going to see it in the next lectures. But just to give you a flavor of what the whole theory is like, here's a good, example of what we will be doing in the course and what are the type of expressions we'll come up with. So this is just for a binary symmetric channel, but you can do it for other channels. And you will have a lot of problems and homeworks and quizzes to see different variants of these problems. So I'm going to write a summary of what we saw and maybe a glimpse of what's coming up in the next lectures. So in the summary, basically, error correcting codes help us achieve perfect communication over imperfect channels. Okay, and anecdotally, 1-bit errors are easier to detect and correct them. Correct than bigger errors. Right? If you have 2-bit errors, then you may not be able to detect it. You may actually detect something which is incorrect. So we saw some basic encoding. / decoding schemes. Right, so we saw repetition codes. Right, one of them is the R3 repetition code, and that gets decoded using majority vote. Okay, we also saw block codes, and one of them is the 7-4 Hamming code. Obviously, can be any NK Hamming code. And we discussed what the syndrome decoder is. So, and finally, we discussed about the trade-off. So there's an achievable rates and and bit error probability. Trade-off, right? So Shannon capacity as maximum rate possible for arbitrary low error probability. Okay, so with that, I think we are done for today's lecture. If people have questions, please let me know.
Yeah, I had a question about arbitrary Hamming codes. Are we always choosing the full number of bits for the code? Is that always double minus one of the signal, or sorry, source code?
What do you mean double minus one?
So like we have 7 and 4. 7 I think is just 2 times 4 minus 1. Is that always the case for all Hamming codes?
No. So that's a
Okay.
good question. Actually, this is this is a natural one because you can map it on a Venn diagram, and that's how,
Okay. Right. This is just an easy way for us to see it graphically.
Yeah. But obviously, you can have more of them, but the parity generation maybe can be different, and again, the decoding has again to be in a matched way. So I there is no formula for the N and K, but people have done different variants of Hamming codes, and they've come up with the matching decoders. So we're not going to discuss them in this course, but just to tell you that there are possibilities, and none of them achieve the Shannon limit. So that's also a interesting thing.
Okay. Thank you.
Yeah. Okay, so announcements, I think, because we haven't covered much until now, so I'm thinking we will have another quiz instead of homework. So we'll have quiz to be held this week. Okay, so homework from next week onwards, and then alternating weeks. And also the other important thing is the project abstracts. So I encourage all of you to start thinking about what you want to do as a course project, and hopefully over the coming weeks you will have a better idea of what the course is like, what you are interested in. So on October 5 or October 4, end of the day, you have to submit a one-page abstract of your project on Canvas. Okay, so it needs to be a one-page description of the idea, papers you will read, and timelines, or your kind of milestones. Okay, so by then, hopefully you would have studied enough to know what's going on, and hopefully you can think of interesting and useful projects. So I think that's it from my end. And if you have questions, you can always send me an email or ask them in the lecture, whatever you prefer.
Are you going to be providing some example papers for the project soon?
I mean, those can be on an individual basis because it depends on what topic you select. If you want, I can suggest to you some good papers.
Okay, I was seeing if there's like a general list that you already have prepared. But that's
I can
okay. Thank
provide
you.
it, but obviously the list of topics is huge.
Right.
So I
Yeah.
don't.
I have
Okay.
a question.
Thank you.
So we're having a quiz next week, and then the week after that, we'll have a homework assignment. And then by October 5th, we have to have our abstract due. Is that the order of things?
No, so the quiz is going to be uploaded tonight, and you will have 1 week to do it.
Right.
Then next week, a homework will be uploaded. You have a week to do it. And then again, a quiz and a homework, and a quiz and a homework. So we keep alternating.
Okay.
And October 4th, end of the day, you have to submit your project abstract. I think that's the 5th lecture or something. Right? 5th or 6th, I forgot.
Okay.
Yeah. Yeah, that's the 5th lecture, right?
Right.
Okay, it's not graded. It's just you know, a selection of stuff that you will read and do, and then you know, you'll have like 2 months to work on your project. There will be a midterm report and then a final report. Okay.
Okay. Thank you.
All right.
Will this quiz be similar to the first quiz with like 10 problems and an hour to do it?
Yeah, similar. So the
Okay.
first quiz was just the modified version of the diagnostic test. So hopefully people who did the first one, you know, should have been very comfortable. And this quiz is going to have stuff from today's lecture, and you know, mostly this stuff.
So we're not going to go back to the lecture 1 stuff, right? Just this lecture.
Yeah, most likely. But obviously there's overlap, so nothing is you know, separable. We're continuing on ideas, right? Like we saw the encoder was there in the first lecture as well. So I mean, there's obviously some natural overlaps, then you have to look, you have to be mindful. But nothing complicated. I think simple questions, multiple choice, right, or numerical answers.
Got it. Thank you.
Mhm.
So 10 questions though, right?
Yeah, 10 questions, 1 hour to do them. And you will have a week.
Okay. Thank you.
Sure. Any more questions? Okay, if not, then let's meet next week, and I'll upload everything, the recording, the lecture notes, and there will be a quiz uploaded. Okay, then have a great week, everybody.
Thank you, Professor. Bye.
Bye-bye.